Hi guys, welcome back to my channel. Today I want to do a chemistry passage from the AAMC Full Length 1 CP section, passage 10. So we have 5 questions that we're going to do after we read the passage. And then the reason I do this video is I feel like a lot of students who just started to learn MCAT, they wonder how MCAT will test you the mastery of the content. And I feel like this passage is really focusing on just the electrochemistry, redox reactions. The content is really not scattered in this passage. So it will be pretty representative how MCAT can test you on certain knowledge, your content, which is very different than how the traditional 4-year undergraduate science education tests us on the knowledge. All right, so let's dive into this. So we'll read the passage. A group of students investigated the reaction of several metals with solutions containing metallic ions. Experiment 1, the student placed strips of metal XX, so this is XX here, into solutions containing different metallic ions. That is a YM plus AQ. So YM plus AQ, this is a metallic ion that's carrying this positive charge, right? M can be 2 plus or 3 plus, M can be anything depending on the metal, right? And then the XX is a different metal, but it is really in its solid form, okay? So that's all I get from figure 1. And then, by the way, if you're not super familiar with electrochemistry, you can watch my video that I dig deep into electrochemistry before we dive into this passage. I will add the link to the description, all right? To the description of the video. All right, let's keep reading. After several hours, they observed whether or not YS formed on the surface of the metal strip, okay? So to form YS, going from YAQ, we need to gain electrons, right? I don't know how many electrons because I don't know the M, right? But this is really reduction, right? Because oil rig, right? Oxidation is losing electron and reduction is gaining electron, okay? That's how you can go from the metallic ion to this neutral solid metal, okay? And then if a Y is getting reduced, it's gaining electron forming YS, Y solid, then X must be the one that's getting oxidized, right? Okay, so that's all I get from so far until here, okay? All right, so table 1. All right, table 1 is the results of metal strip experiment, okay? All right, so basically table 1 here says identity of metal ions, right? So this is all these are basically the YM plus, right? In its aqueous form. Whereas here you see the composition of metal strip. These are the solids, right? So these are really the XS, right? All these, okay? All right, so I'm not gonna look into every single square of my table to do the comparison to analyze, okay? I would just try to get a general feeling what is this table, what does this table tell me, and then I'll move on, okay? If I need specific information from this table, I can, when I read the question, I can later come back to the table and look for the specific information I need. But for now, I'll just get a general understanding of this table, okay? So let's just pick, let's say zinc, right? When the solid is zinc. So basically, if this is my beaker, and then I have this zinc solid metal strip, right? And then let's say I will have this copper, right? And then my ion will be Cu2 plus AQ in my solution, right? And then we see that as time goes by, there's a new solid that gets formed, right? So the new solid must not be the old solid that is the zinc solid. There must be the copper solid that's the new solid, right? So like I said again, the ions will have to gain electron to form the neutral solid form, right? So in this case, I'll say, okay, so what this tells me is that zinc has a higher reduction potential. I mean, copper has a higher reduction potential than zinc because copper, in this case, is the one that's getting reduced, the one that's forming the new solid, right? And then zinc, on the other hand, is the one that's getting oxidized, or I can say zinc has a higher oxidation potential than copper. Okay, so that is the information I can extract from this table, but I'm just doing this one example for you to get a general understanding of the table, but we're definitely not like digging into every single square to do the comparison to see, oh, which one has a higher reduction potential, which one doesn't. Okay, all right, so we will just keep reading the passage. Okay, all right. So the passage says experiment 2, okay? Experiment 2, the students place a solid strip of each metal into an aqueous solution containing ions of the same metal. Complete circuits were established, okay? So figure 2 is this a complete circuit, and then it really looks like what? It really reminds you of the galvanic cell, right? And then you have to be a galvanic cell instead of electrolytic cell to make this a circuit, right? Because you want to have the spontaneous electron movement, electron flow to make this efficient circuit, right? That will have this current flowing that will light up the light bulb, okay? All right. And then we keep reading. It says, finally, the students checked a general chemistry text to determine the standard reduction potential for the following reactions. Okay, so reaction 1 is PB getting reduced to PBS, and then the reduction potential is really quite low, right? It's negative 0.127 volts, right? Whereas reaction 2, this copper getting reduced to the solid copper has a higher reduction potential of a positive 0.339, right? Meaning that if it was a spontaneous redox reaction, I would say that copper is the one that's getting reduced due to the higher reduction potential, and then the PB will be the one that gets oxidized. Okay, so that's all I get from the figure from the rest of the passage. Okay, all right, now let's dive into the questions. Okay, so question 52 says a student can most effectively increase the current passing through the circuit in figure 2 by doing which of the following. Okay, so let's go back to figure 2. All right, so figure 2 is this very much like galvanic cell setup, right? And then to increase the current flow, basically we know is to increase the electron movement, right? To have a very spontaneous redox reaction, right? It doesn't matter like which side is doing oxidation, which side is doing reduction. We don't have to know that, right? We just need to know that generally, if we were to increase the current flow, that we really want this one to be very much spontaneous, right? Okay, let's see. So A says, using electrical wire with a smaller diameter. Okay, so this sounds like the opposite of increasing the current passing through the circuit, right? Because really, if you decrease the diameter of the wire, it really kind of inhibit the current from flowing through, right? So I would say A is maybe not. Okay, let's just keep reading. Okay, B says increasing the temperature of the electrical wire. Okay, this can be a really good distractor because a lot of students would think, okay, increasing the temperature will speed up anything, right? It's always beneficial to increase the temperature. Okay, because in terms of a kinetics of the reaction, yeah, true, increasing the temperature can speed up the reaction, but here it's not asking about whether to increase the speed of a reaction or not. It is to increase the current passing through the circuit, right? So B really does not necessarily increase the current passing through the circuit. So I would say B is probably not as well. And then C says decreasing concentration of Xm plus AQ and Ym plus AQ. Okay, so this is really being ambiguous, that not telling me what is X, not is what is Y, what is X, right? But it doesn't matter, right? Because decreasing the concentration of X and Y, we know that it would basically decrease the redox reactions, right? And then this will really decrease the electron flows if it was, spontaneous redox reaction. So I would think decreasing the concentration, aka decreasing the reaction, that will decrease the electron flow, and then that will decrease my current passing instead of increasing the current passing. Okay, so I think C is probably not again. And then let's read D, hoping that it's a better answer. So D says, replacing the light bulb with one that has a resistance of a 0.2 ohm, okay? So as you see here, the light bulb, it got lit up. It does get lit up because of this spontaneous redox reaction. And then there's a spontaneous electron flow that will power up this light bulb, right? It's basically like a battery, right? It will light up the light bulb. But this light bulb itself, having this electron flowing through it, this light bulb itself creates some resistance, okay? It kind of inhibits the current flow and then the electron flow, okay? So originally, the light bulb has this resistance of a 0.5 ohm, right? And then if I now replace the light bulb with the one has a different resistance of a 0.2, I am decreasing the resistance, right? And then decreasing the resistance, very intuitively, you can imagine that will increase the current passing through the circuit, okay? So I really like D, and I think D is the best answer, okay? All right, question 53. When a stripe of zinc is placed in a beaker containing 0.1 molar HCl, H2 gas evolves. If a strip of Al is placed in a beaker containing 0.1 molar HCl, does H2 gas evolve? Okay, so there's many facets of this question stem that we need to break down. Okay, so first, let's say, okay, I have a beaker, and then in there I have this zinc solid, right? It's a strip of zinc, okay? And then I have a 0.1 molar HCl. And then in the solution, my HCl will really be broken into H plus and Cl minus, right? And then it says H2 gas evolves. And then for H2 to evolve, we need to give this H plus an electron, and then that will become H2, right? And then this H plus gaining the electron really means what? Really means this H plus is getting reduced, right? Okay, then if H plus is getting reduced, we know that the zinc is getting what? Is getting oxidized, okay? So this is what's happening, okay? And then the question asks if a strip of Al is placed in the beaker, okay? So now in my beaker, I don't have this zinc, I have this Al solid, okay? It's also containing 0.1 molar HCl, okay? So I have a H plus, Cl minus. Does H2 gas evolve? So basically it's asking, does H plus in this case gets reduced as well so that Al gets oxidized? Right? That is the question. If we were to simplify it, that's what the question is asking, right? Does Al get oxidized, right? But we don't know, right? We only know that zinc did get oxidized. But what about Al, right? We don't know. So before I dive into all the answer choices, I'm just guessing, I'm just guessing that I'm hoping that Al would have a higher oxidation potential than zinc. Then if zinc did get oxidized, Al with even a higher oxidation potential would definitely get oxidized. Then I can choose A or B. I can choose yes, right? Al is oxidized, okay? So that is just my guessing, but I don't know, okay? So I need to go back to my table, okay? To my table to really compare zinc versus Al. Okay, so I'm gonna do my comparison now. Okay, so I'll use a different color. Okay, so zinc, let me find zinc. Okay, so I have a zinc here, and I have Al here. It tells me no change, and then I don't like it. Okay, so I'm gonna find Al here, and then zinc here. Oh, I see new solid, right? That's more confirmative than the other no change, right? It really doesn't tell me something like something I can apply to my question, right? Okay, so in this case, it tells me that I have this Al solid, right? And then zinc 2 plus forms zinc when it reacts with when you have zinc ion in the beaker, it forms new solid, right? So this new solid must be what? Must be zinc solid, which is the new solid. The old solid is Al solid, right? Okay, so this means zinc gaining electrons, meaning what? It's getting reduced, right? And then on the flip of the on the other side of the coin, you can say Al is getting oxidized, right? Okay, so if zinc is getting reduced, Al is getting oxidized, that says what? That says Al has a higher oxidation potential than zinc, right? Zinc has a higher reduction potential than Al. So that's why zinc is forming new solid. Zinc is getting reduced, and then Al is getting oxidized. Al has a higher oxidation potential. Okay, so this actually confirms my assumption, my expectation, right? But I really can't just make assumption and pick A or B or whatever. I really have to go to the table and then confirm my expectation, right? And then so in this case, yes, Al is oxidized, right? And then H plus is reduced. Okay, so B is my best answer. Okay, all right. And then question 54 says, assume that a circuit similar to that in figure 2. Okay, so let me remind myself. Okay, figure 2. This is what figure 2 looks like. It very much looks like a galvanic cell, right? Okay, so a circuit similar to that in figure 2 is set up in which X is Al, X ion is this Al ion, and then Y is this copper, and then Yn plus is this copper Cu cation, right? All right, which of the following reaction will occur? So let me plug in all this to my figure 2, okay? So the question says X is what? Is Al solid, right? And then this ion is Al 3 plus Aq, okay? That's what the question tell me. And what about Y? Y is the Cu solid, right? Y is the Cu solid. And then Y ion is the Cu2 plus Aq. Okay, so that's what the question told me. Okay, now I have to figure out the reaction that's happening, right? But I don't know which one is getting reduced, which one is getting oxidized, right? But we know that it's a circuit, so it must have a spontaneous redox reaction. So I will go back to my table and then see if I can figure out which half cell is getting oxidized, which half cell is getting reduced, right? So let's see. So I have a zinc here, and then where's Al? Al's here. Oh, it's giving me no change again. I don't like that. Okay, so let me actually find Al. Find Al here, and then where's my zinc? Zinc is okay. Zinc forms new solid. So as this example tells me, now you should be familiar with this. That you know, okay, zinc is the one that's getting reduced, right? Zinc is the one that's getting reduced, and Al is the one that's getting oxidized. Okay, so now I can really, according to this, I can write out my half reaction. So my half reaction, oh, it's actually comparing to copper. Okay, that is okay. Copper is fortunately also getting reduced. Okay, so if that's the case, we can write out the half reaction that copper 2 plus is gaining electron, forming copper solid. Okay, and then what about Al? So Al is the solid that's getting oxidized, forming 3 electrons plus the Al aqueous ion. Okay, all right, so these are my half reactions, right? One reduction reaction, one oxidation reaction. So from the reaction, if I combine those together, I mean, I can just cross out the electrons, then I know that it is the copper aqueous form that's combining with the Al solid form, right? So I can rule out A and B, and then it will be C and D, right? Because C and D, that matches the status, right? This is solid, this is solid, this is AQ, this is AQ, and then the other side, this is AQ, this is AQ, this is solid, this is solid, right? So C and D really match us up, right? If I were to add up these two half reactions. And then the only thing we need to do between C and D is to see which one is balanced, right? And then obviously C is the one that is balanced, right? Because here you can see that these are neutral, right? But these charged ones, I can see this is positive 6, this is positive 6. But if you see D, then you will see that this gives positive 4, but this gives positive 9, right? Okay, so C is my best answer. Okay, all right, let's move on. Question 55. A circuit similar to that in figure 2 is set up in which X equals PB. Okay. X is PB, X ion is PB2 plus, Y is Cu, and then this Y ion is Cu plus. Okay, will an oxidation reduction reaction occur spontaneously? Okay, perfect. So I mean, this PB and Cu, basically this tells us the reduction potential of these two different metals, right? So we know that, okay, for this to occur spontaneously, we want Cu to be reduced and the PB to be oxidized, right? So their cell potential equals to what? Equals to the reduction potential plus your oxidation potential, right? And then the reduction potential of the side that's getting reduced is a positive 0.339, right? And then plus the oxidation potential of PB, right? Then we need to flip this because this is really the reduction potential of PB, but now PB is getting oxidized, so it's really positive 0.127. Okay, so plus this positive 0.127. So my answer will be some positive number that I don't even bother to calculate because I know that between C and D, the negative cannot establish, right? When it's negative cell potential, then it's really in an electrolytic cell that is not having the reactions occurring spontaneously. Okay. So that's question 55. Okay. Now let's look at question 56, the last one. Okay. It says a circuit similar to that in figure 2 is set up. Okay. So what is figure 2? Okay, figure 2 is here. Okay. This is my figure 2. And then it has a potential of 2 volts, okay? So because figure 2, I'm assuming that this circuit, right, it's having spontaneous, like a galvanic cell, spontaneous redox reaction. So that's how it can produce the potential of 2 volts, right? 2 volts is really a positive, this E cell potential, right? That volts is the unit for the cell potential. So basically we can put volts here, right, for those cell potentials. So a potential of 2 volts. So it's spontaneous, right? That's why it can cause a current. It can light up this light bulb. All right, let's keep reading the question. Assume that the resistance in the circuit is negligible compared to that of the light bulb. So you're telling me the light bulb's resistance is not negligible, right? So approximately how much current passes through the light bulb? So this is really asking you how much amps of this current, right? And then the equation is volts over R. And you know that V equals IR, this Ohm's law, right? And then you just rearrange it and you get I equals a V over R. And then what is V is 2 volts, right? And then what about R? R is 0.5 ohm, right? And then that will give me 4 amps. So my answer choice is D. So that's a taste of what how MCAT tests content. And then it really requires very, very deep comprehension, very solid comprehension of the content for you to really solve all the problems correctly under roughly 8 minutes per passage. I hope that's helpful.